and then it's autofocus. So that means if somebody walks in front of them, it's not going to go out. Trust me, I have like 4 semesters worth of experience.
Definitely got the pros and nice ministry.
Yeah, I got to do this for clients class. I got to put that guy on display.
Dude, he's also like someone just wanted to go just because he can't. He's
So what I'm going to do is going to set up like an attachment to my backpack. Just put my backpack. Yeah.
Like,
Fuck that guy.
I don't see why he wouldn't be alright with this. It's like if it's on the desk or somewhere else or like sitting back like you said, like you're not on the internet.
Yeah.
You're obviously just trying to get the lecture.
I'm trying to.
Why? 1 or 2?
Yeah.
1 or 2.
On the requirements, you don't have any boiler requirements.
No, I didn't.
And the pitch distance is 1.75 inches for a superheater with a 3.5 diameter pipe.
Oh. Am I violating laws of physics? Yeah. All right, I'll have to adjust that.
Do we get like credit for that since we?
One at a time. What was the question?
There's on the report, it says the maximum allowed pipe diameter from the boiler to the turbine is, and it just like dropped off.
Oh, I left you in suspense?
Yeah.
12 inches.
Well, we get to fill the blank.
Aside from all this,
Aside
that's a
from
real
all that.
question. So for the
Okay, aside from something that needs to be fixed in that worksheet that I gave you, what else have you got?
okay, for the actual boiler portion, do you have to figure out all 3 of the phases in the middle, or just the pool, and then how do you add that together? We don't have that.
No, you will.
Oh,
This is what I was working on in Spain.
I sent you to Spain to do that, huh?
Spain, there's a lot to recommend for Spain. First of all, it was actually was a great trip,
It's not
aside
showing.
from the fact that I had to come back to the lynch mob.
You gotta bend it from here.
All right, we have a boiler. You'll notice 6 pages. It's very involved. This is
How many pages is that?
6.
That's it?
And
With
those are just the
references?
I'm so excited.
Now,
Kakak and
if
Lu.
we reference your paper, do you want us to reference all your references and our references?
Or you can say, you pirated this from one Richard Ayala. This is a boiler sizing. The problem with boiler sizing is that you're dealing with 2-phase flow. And I think when we were talking about it, I did talk about the correlations that you have with 2-phase flow. So here we have a little schematic for a boiler. I've given you some description of what's going on. We have a boiler that's considering a mass flow rate of some flue gas, and we have a generation of steam, and then there's some dimensions of our enclosure, and some temperatures coming in and coming out that come from a temperature duty diagram, some pitch distances, and so on. And then there's some details of the design, and we come up with a number of transverse tubes. That's all that we've done. This should be the same as what we did for the superheater, which was posted. Tube-side heat transfer. This is where it starts to get a little interesting because we're going to convert water into steam, so we have to consider 2 portions. These are brand new, by the way.
Lick the tip.
Wow, okay, that's better. diagram that you have learned to love.
So that,
So we have the pump exit, saturation. So we're dealing with heat transfer into this portion. So there's two portions of it. One will be sensible heat transfer, one will be latent heat transfer. This is all captured in here. All we're doing is essentially calculating the rate of heat transfer from the flue gas into the steam, and that turns out to be about 35 megawatts. No simple formula. I gave you this expression, seems like ages ago, but I gave this to you when we were talking about boiling and condensation. This is essentially a quick correlation to go ahead and calculate the heat transfer due to the boiling, where the C sub I is the single phase convection heat transfer. The B sub I is what we would calculate using, what do we call that? Nuclear pool boiling. So the first thing we would do is calculate this based on the feed water properties. So this is the Reynolds number coming in. We go ahead and calculate an Asselt number, calculate a convection coefficient. This is for the single phase feed water entering the boiler. We would then calculate a heat flux using the correlations from that we talked about in boiling and condensation. We're dealing with a polished stainless steel tube. We make a guess for the excess temperature. We calculate a flux. We calculate the boiling convection, where I'm essentially considering this per tube. I have 60 tubes in the transverse direction, so I'm getting a flux per tube. I would plug this in to this expression, and this gives me my convection coefficient for the inside of the tubes. For the outside, I have two portions. One is straightforward from convection from the gas. There's going to be a convection portion and a radiation portion for the non-luminous radiation. This is straightforward, just normally what we do. For the non-luminous, we have some correlations. Like I said, this will be posted on Blackboard, so don't worry about not having a photographic memory. But we calculate the non-luminous contribution as well as the convection contribution. And with this, we would calculate the overall in terms of what's happening on the gas side, on the steam side. We calculate an area and we calculate a flux. This corresponds closely to what we calculated before. So what you have to do is adjust this guess here for the 9 degrees until you get a close correlation between these two.
what to,
And then once I've got a satisfactory correlation, I can go ahead and calculate the number of longitudinal tubes, calculate the total number of tubes, the longitudinal distance, and I'm well on my way. Easy, right? 6 pages later, we're done.
How did you determine 62s?
At the beginning, I know the dimensions of the duct. This is given as L sub W, L sub H, and these were specified. And then I know that I have a number of tubes. In here, the tubes have a certain diameter, and they're going to have a certain pitch distance. So I would essentially look at this as dividing it by the pitch, and From that, I was able to estimate about 62.
Question.
Yeah.
When you solve for that rate of heat transfer, is that the same rate of heat transfer you use in the combustion analysis to solve for the mass flow rate of the flue gas?
Were you saying this one here?
Yes.
Yeah, this is just for the boiler. So remember, depending on what your system looks like, imagine, for example, we had a power plant that had superheat. And let's say reheat. Right? When we were doing the combustion calculation, you used all of it. You used what's going in the boiler and what's going in the superheater and the reheater to calculate the overall heat required. Because that's going to determine the mass flow of the gas and the fuel requirement, right?
So does that mean it's Q in then?
That's Q in when you're doing the combustion calculations and the overall. When you're looking at the boiler, you're only going to be looking at this portion. So for the boiler, all we're really looking at is the value here at saturated vapor, and whatever value is coming in. So we're looking only at the heat transfer that's taking place in the boiler. So like I said, this is not the total heat addition for the overall system. The heat exchanger, reheater, if you have a superheater, if you're looking at, say, the superheater, you're only going to be looking at this piece. If you're looking at a reheater, you're only looking at that piece. Any other questions?
The boiler is not required, right?
I'm sorry, what?
The boiler is not required.
The boiler? Well, your system has to have one.
Yeah, but it's not in the assignment.
Did I not specify that in there?
Too late. Too late. You dropped the ball. It's too late.
In the corner, aren't I? You guys are finding a loophole, and it is late this semester. This is true.
Extra credit.
Are you recording this?
This is FaceTime. It's Skype.
2 semesters of that thing there?
You should look at funnyteachers.com. No, I'm just messing with you.
I think you mean handsome teachers, of course.
I found myself on drawmyprofessor.com.
Really?
All right. Were there any other questions? I know that what I did tell you all is to monitor Blackboard in my absence because I have added things to there. One is that I added a reference on doing the pump characteristic curve and sizing. And then the other thing was that the Excel sheet for the economic evaluation is posted, and some guidance is also posted with the Marshall and Swift index that I want you to use. There should be the superheater sizing calculation is posted. The condenser sizing calculation is posted. And that, I think, was there. Okay, were there any other questions? Yeah.
So if you have four heat generation sets, 2 of them are on feed water and 2 of them are not. So the water coming out of the feed water heater is obviously warmer when it's getting pumped in, and then it's mixing with the cooler water. How would you marry those together?
How would I marry them together into what's going into the boiler?
Just do an average?
Yeah, take an average.
Okay.
We're not going to be terribly sophisticated in this course. Now, I would have to warn you that we have simplified this to the nth degree for the purposes of this course, and the real world, quote unquote, it would be a lot more involved.
You'd have more than a semester too.
Huh?
You'd have more than a semester to figure it out, I'd imagine.
I would say
Well,
5 years.
These methods that I'm giving you are highly simplified. And unfortunately, like I would say, if you were to, what is technology? If you were to look at some of these references, they are somewhat dated. And that is because in order to find a lot of these correlations that I'm using, they're somewhat passé. In other words, they moved on to more computerized techniques that don't lend themselves to this course, because its software tends to be proprietary. So I'm kind of giving you some older techniques that lend themselves to hand calculations and things like that. And a lot of them are highly simplified, so they're not going to be industry norm by any means, but they serve for purposes of this course. So, yeah.
When you're taking in the heat transfer between in the condenser, between the tubes and the shell, if we have a steam trap that goes into the condenser, do you just add that in when you're calculating the heat transfer on the steam side? So you basically have the flow rate coming in from the turbine and coming in from the steam trap.
Oh, okay.
Yeah.
What you're saying is I have a condenser, I have what's coming in from the turbine, and then I have the trap, and it's doing this. And then I have the output, and then on a separate loop I have the cooling water. Correct? Yeah, I would just take those two and lump them in as one inlet. Yeah, go ahead and take them in for an average.
So that's another question. We have, we're getting a really high heat transfer between the steam on the shell, or in the shell, and the water in these pipes. It's causing the velocity on the tube side to be really high. I know you set that to 2 meters per second. I'm not sure how to remedy it, because I guess the only way to change the velocity, or I guess the heat transfer, is, I have to think about it.
Right? And what you're saying to me is that this Q is getting really high?
Yeah, it's really high, and when we try to find the flow rate on the tube side, it's coming out really high. So the velocity of the water is way past 2 meters per second.
Right. And what would you like to do? Would you like to reduce Q dot?
I would like to use
Reduce this.
so we can, okay.
And how would you reduce that?
The pump. See, yeah, the thing is,
Split it into two.
how many condensers do we
Have I given you a limit?
Yes. Right? One
Did I?
for one generation set.
I said you can have one, I put you a limit on the turbine generating sets, right? But I didn't specify how many condensers you can have. You can have multiple condensers in order to make this work. I just don't want you to solve the problem by replicating one, 50 turbines, for example.
Man, it's good mind games.
Well, our original design, basically, it's basically running around the same loop twice, if that makes sense. Our whole, the ramping cycle, so basically everything's double.
Everything's doubled.
Yeah.
You have, what, 2 loops?
Let's say that. Not sure if I'm crazy.
Well, I guess what I'm saying is you have some flexibility to think outside of the box, if you will. So for example, if you're having a problem where you're finding that you have an excessive amount of heat transfer, remember that if I reduce the mass flow rate for the same conditions, I can reduce the amount of heat transfer, which means I can make this condenser a little more reasonable. So I can have 2 or 3 reasonable condensers rather than trying to come up with one gargantuan monster condenser that nobody in the world could build. And if you do something like this, for example, you would only have to do the calculation for one of them and present out. I don't want to see, 30 calculations for the same
You
condenser.
just mentioned that we have.
Yeah, you would specify that that's what you did. For example, the way you would treat this is that you can explain to me, we ran into this problem, and in order to solve it, our solution was to employ whatever. You could do a little parametric study and see what rate of heat transfer is tolerable that you could design a condenser for within, say, the package limitations that I've given you. You could then go back and say, okay, we need to take this and maybe use 3 condensers. 3 identical condensers. We're going to show you the sizing calculations for one of them and just explain to me that that's how you solve that particular problem. Okay? Just like some of you were using multiple pumps to get the mass flow rate up, that again is a perfectly viable solution as long as you can explain to me that after pondering, we decided to do this, and lo and behold, it worked. And it was within the overall constraints of a design problem, just like this would be. Because you're not giving me like 20,000 turbines or something like that. You're essentially tweaking this to make it work. Yes, sir.
Can you use that same principle for closed-feed water heaters? Having multiple closed-feed water heaters and lowering your M dot through them?
Yeah, if you're finding that, because it's essentially a shell and tube type of thing, it's still a condenser. So if you're finding that your mass flow rate is exorbitant, or it's requiring that you have a huge amount of heat transfer, yeah, you can use 2, say for example, divided into a couple of feed water heaters. Just like I said, present. During our studies, we found this particular problem, and we solved it by doing this, without making it a lengthy discussion. And like I said, if you're doing, like if you're having 5 identical feed water heaters, I only need to see the sizing calculations. Or even if you're doing some that are, even if they're slightly different, if it's the same calculation, so I only want to see one representative calculation. Any other questions?
For the economizer, is that a requirement or was that an option?
That was an option. Just that if you're not using it, you have to account for that heat addition somewhere else. Because what an economizer is doing for you is it's trying to capture some waste heat to use it to preheat the water. It's sort of like a feed water heater. Feed water heater is designed to preheat the feed water before it enters the boiler. The difference is that in a feed water heater, you're using the steam to preheat the feed water at the expense of some power output. And with a economizer, you're using flue gas to do it at the expense of having to build a secondary heat exchanger. So, and also also, you're somewhat limited because by the time you use it, you pretty much extracted all of the energy in the flue gas to the point where there's not a lot there, and there's a limit to how much you can successfully get with an economizer. Any other questions? Yeah.
Was a physical schematic of the plant something you wanted on the report? Like actual spacing and placement of each of the parts?
What I want is thumb drive worked. Before I left for Spain, I gave you some schematics of we have the typical design for a turbine. You know, what I want is something that I can see your system laid out. Something somewhere in between a crude hand sketch and a super elaborate design. Something where I can see your state, see your system, identify the states, tell me like the pressures and temperatures of each one, and go through it. If you have, for example, 4 identical systems, then what I would like to see is a detailed sketch of that one system, and you're just telling me that there's 4 of them. I would like to see some standard conventions. There are a lot of good, I notice a lot of you have used images that you've obtained from the internet, which is perfectly fine as long as you clean them up and adjust them so that they're germane to your problem. In other words, if you're going to grab images from the internet, edit them so that I don't see temperatures and pressures that aren't not in your problem, for example. Because it makes it a little bit confusing for me to evaluate it.
Well, what I meant, for instance, is like
So I want detailed dimensions, and you're showing me all the pitch distances and the diameter. In other words, do I want a scale drawing?
yeah. Well, just like for like the important parts, like the piping in between each of the components. So like from the turbine to the condenser to the boiler, piping there. If you want dimensions on the piping, on how long it is, and if there's like angles or specific.
Like for the boiler, I have this little cartoon that I put together. I don't expect you to go to that level of detail. Something.
Just for not just for the individuals, like not just boiler, but the
Okay.
the pipings in between.
In other words, for example, you're saying, here I have my superheater exit, and here's the turbine set.
Right.
And your question is, okay, I've got a pipe and it's going into the turbine.
Yeah.
And you're asking me, do I want a super detailed?
Well, just the dimensions of it.
Yeah. For example, yeah, it would be sort of like, something like that would be sufficient.
If it doesn't go at 90 degrees, like 45.
Yeah. In other words, if you're saying, okay, I'm going to put a 45 elbow here and a 45 elbow there and do something like that, that's fine.
Okay, and that would be with the overarching.
Yeah, that would be like an overall, like the 10,000 foot altitude snapshot of it, where your components don't have a lot of detail, for example, and so block diagrams. If you looked at the report handout that I gave you on the back, it kind of had like a little schematic.
Right.
Something like that would be where you would just scale it, put some overall dimensions like that. So something like that would be exactly like that.
I mean, this one?
If it's germane to your system, yeah. Like for example, if you want this little boiler picture, it's available for a nominal fee.
I was wondering if you could maybe explain a little bit your schematic for the boiler superheater. Like up there you have, obviously L.H is gonna, or LH is gonna be 22 feet on your schematic. The 18 feet, I'm not too sure what exactly it's referencing, if it's the LW or.
Can I borrow that sheet that you have? No, it's just that my thumb drive doesn't work in this computer for some reason. Okay. Okay, my boiler, correct? And I'll say, for example, that in front of it I have a superheater. And I have and this is the boiler. And then what I've said is I have a duct. That's okay, is that clear enough? So this is sort of like an isometric sketch. The flow, the gas is moving in this direction. This is the superheater, so I would have feed water coming from the boiler, coming in here, and it's then going through like this, coming out here, and then the gases are coming out through here. This would be what I'm calling L sub W. This is L sub H. And then if we were looking at the boiler, for example, this would be L sub D. L sub D is something that you would be calculating for each component. L sub H would be 22 feet. And then L sub W I have is 18 feet. And then so continuing, he says that this is 18 feet, 22 feet, and then this dimension here would be 18 feet and 18 feet. So here's where I have the flue gas going in another direction. Here's where I have the furnace, so the flue gases come from that direction, they flow in this direction and out in that direction. And the way I've drawn it, I had superheater here, and then the boiler there. So the duct is 22 feet high and 18 feet wide. And then if you're utilizing this space for some kind of a heat exchange component, it is a square duct 18 by 18. Does that answer your question? Okay. Thank you.
Yes, sir. Point of confusion that I know a couple of people have is the exit temperature of the flue gas. if you don't have an economizer or anything like that, what would it, you don't have any cooling agent or cooling anything after the boiler, it's not hitting anything after the boiler, right? Is that just?
Yeah, then you're
That's
discharging whatever that temperature would be.
Okay.
Hence, it's a wasted energy. This is why people incorporate other heat collection devices. Because you're exhausting at what? If you don't have an economizer, you're exhausting at the saturation temperature plus 20 degrees, roughly.
Yeah.
That can be pretty high. So that's why they typically install a economizer to capture some of that energy.
But if you're good with that, with wasting all that energy, you're good with that.
Well, it's not that I'm good with it, it's, should give
That
me your
means you're
proposal.
good. That means that 20 degrees over the dew point temperature is not even in question at that point.
Oh, yeah, you're not gonna, you're nowhere near that.
Yeah, okay.
But the problem is it's wasteful, because remember, now you have to essentially generate steam from you're basically generating your steam from the fuel. Whereas before, you're utilizing a lot of it to get to to heat it from a certain temperature, and you're using the waste heat to preheat it up to that temperature. In other words, without an economizer, you're heating from here up to there, right?
Yes.
If I use an economizer, I'm capturing this energy, and I'm heating it from somewhere else. So just like with a feed water heater, I'm reducing the heat addition, because when I look at Q dot in,
Yeah.
and I'll just use it from the saturation point minus HF, or we'll call it H naught prime, or where I'll call this H naught, or H naught prime.
If you've already met the specifications and you've approved the design or whatever, can you then go back and still add an economizer if you want it, or?
Yeah, I don't have any problem with that, just tell me why you're doing it.
Because I don't want to kill the pay one to me,
Huh?
What's the downside of using an economizer?
Money, it's one more piece of hardware that you have to pay for. You remember the economic analysis that I gave you? It's a piece of equipment that you now have to go out and buy and size and design. So there's engineering time to develop it and size it. You've got to go out and buy the thing. You've got to maintain it. You've got to clean it. So there is a cost of having one. It's essentially a capital and a operations maintenance type thing. Or you could eat the cost of the additional fuel burn to not have it. So you kind of have to do those trade-offs. Yeah.
When you're trying to find properties of steam going across a condenser, in one of your examples, you took the bulk temperature,
Mm-hmm.
but in the TS diagram, the condenser, you're basically at that bottom line, which shouldn't be any temperature difference. Or do you actually take it coming up from the top right?
Yeah. When you're in the condenser,
Yeah.
I just may not have the darn thing in here. Oh, because in this case, I'm not evaluating the properties of the steam, I'm evaluating the properties of the feed water, of the cooling water, rather.
So the water coming from the municipal water?
Yeah, in other words,
Yeah.
if you look at the the condenser sizing example, I'm calculating T bar M. That is for the cooling water.
Oh, we might not be looking at the same thing.
I'm looking at the one I said condenser sizing.
Condenser sizing?
Shall I show you? I'm sorry. It's this example.
That's, okay, that's a heat exchanger.
It's not necessarily a condenser.
No.
Okay. Okay. All right. So technically, there shouldn't be a bulk temperature across the condenser. It's just
There's two streams when we're dealing with a condenser.
That's right, yeah.
One of them is the steam that we're condensing, in which case the temperature doesn't change.
That's right, okay.
And then the other one is the cooling water, which does change. We have to account for that. Any other questions? Yes, sir.
In that condensing sizing problem, you found the tube wall thickness as TW. I don't know how you found that.
It was given.
I know, but you gave .0028 when I calculated as is what the inner and outer diameter of the tube.
Oh, okay,
Should
yeah.
be .005. I don't know if that was a typo.
It's probably a typo. They're doing Microsoft Word. And the fact that I have this thing set up to be interactive, so if I don't update everything correctly, it kind of has a hiccup. Is that on a condenser sizing example?
Yeah, it's in the problem statement.
I see it's at 00287.
Yeah, and I calculated .0058.
I'll have to go back and double check that, okay. But effectively, yes. Oh, and I also posted some additional TIMA standards with some additional diameters on Blackboard. I think before it was only up to 39 inches, now I've given you up to 60 inches in terms of the shell diameters for tube counts. That stuff is also hard to find, believe it
Tube
or not.
shell outs, layouts on.
It is. And the only way I was able to find those is to go back and find some ancient texts or ancient references, so I don't know why that stuff's not.
In the problem, in the specifications, it says that we have a 15-foot shell diameter, but the new TIMA standards still don't specify that shell diameter. How can we calculate the number of
I
passes?
have been trying forever to find that. Because there are some equations that allow you to estimate tube size that I gave you before, where you can calculate it, using some other things. That's one way of doing it. The TIMA, I have found some tables that do go a little bit higher on the TIMA standards, but they're incomplete, so I don't have to pay for the entire spectrum and the entire tube diameters and pitch setup, so that's why I don't have that. One reference that I had said that there was actually an equation that they now use to calculate that stuff, but I have yet to be able to find it. This stuff, and I think it's simply because, like I say, a lot of this stuff is computerized, so a lot of these tables are become defunct.
For the final report, do you want all of the state calculations put back into the report, for the interim report?
The state calculations?
Yeah.
Thermal analysis.
Thermal analysis.
Yeah, because there's probably going to be some changes. For example, you're adding some things, and I imagine that some of you may have had to change things as you work through your problem.
So far, we're golden.
You're golden.
No.
I did post something where I was talking, where I gave it was, let's see, it was a thermodynamic analysis that combustion calculation, then there was a temperature duty diagram calculation. Did everybody see that one? No. Find the books and you just. Posted something on.
Do you calculate the superheater and the reheater as one thing, or is that two whole separate
They're
calculations?
two different calculations because a superheater doesn't involve a phase change. Oh, you talking about superheater, reheater?
Yes.
They're separate devices, and they'd have to be sized differently, or you have to size them. The analysis is the same.
What comes first, the reheater or the superheater?
Well, that's up to you. I posted this on Blackboard. This again was just like I said, it was a thermodynamic analysis. Of a hypothetical plant where I went through all of the state calculations. And again, this is on Blackboard. And then there was the cycle analysis of all the bits and pieces. Then there was a combustion calculation.